What's up, calculus students? Lesson 4 is like other derivative questions. And it's a tricky one, this one. The last two are the trickiest ones of the entire unit. If you thought the product and the quotient rule was tough, do it with sine and cosine, do it with secant and tangent and stuff like that. We also have notational derivatives, which you guys stink at because you don't like to use notation ever. We also have these, what does it mean to be differentiable? Differentiability problems. We use piecewise functions with it. We also have these higher order derivatives. There's a lot of stuff in here. Now, I'm going to get you started with just derivatives of these other trig functions, but paying special attention to what's going on here, okay? Doing this on purpose because we make a lot of mistakes when we deal with constants. Just because we see a constant times something, we don't use the product rule. Okay? Just like if I had 4 times x cubed, I wouldn't use the product rule. I would just take the 3 and multiply it by the 4, right? Or the 4 would stay out there, and then you'd have 3x squared. If I have 4 times a function, the derivative is 4 times the derivative of the function. This is very important, okay? That's the first thing. Second thing is just because you have a constant in a fraction does not mean you have to use the product rule, the quotient rule. Because it's not x's. You don't have x's times x's. You don't have x's divided by x's. You don't have to use a quotient rule. What I would recommend, and this is the same thing with like f of x over 4, is think of this as 1/4 times f of x. It's just another constant times a function. The derivative is just 1/4 f prime of x, or f prime of x divided by 4. Okay, so that's the first thing we need to remember, and this is very important for later with the derivative rules, that if you don't have x's times x's, just leave the constant. Here's y prime. Take the derivative of secant. Derivative of secant you need to know is secant x tangent x. This will be given to you for the next quiz and the last quiz, but not for the test. The derivative of tangent is secant squared. Again, I would rewrite this as 1/8 times tangent. The derivative function would be leave the constant, take the derivative of the function. This is very, very important, especially later with notational derivatives. Let's do this one. Let's do this one, and then we'll do the tougher ones. Cotangent x over 4. Okay, I'm going to write that as 1/4 cotangent x. Now, I just rewrote it. I haven't taken the derivative yet. Don't forget to take the derivative. A lot of people, when they simplify, they forget the next step is to then take the derivative. Simplify first to take the derivative. Derivative, the slopes of cotangent are negative cosecant squared. I'll put that negative in front of the 1/4. Cosecant squared. Remember, cosecant squared is cosecant x squared. 3. It's not x's times x's. It's a number times x. Numbers times x's. You don't have to use the product rule. We just leave the 3. The slopes of cosecant are negative cosecant cotangent. It's negative cosecant x cotangent x. A lot of students make mistakes by putting just like cosecant cotangent like that, but make sure you have cosecant of x times the cotangent of x. Okay, now I honestly should have an extra one down here. H of x equals 3f of x. And h of x equals f of x over 3. I'm going to throw those in there as well. Now, the remaining ones, we do see, and we did this in our notes, x's times x's. Yes, we need to use the product rule. Here, x's times x's. Yes, it's x divided by 3, but again, I'm going to write that as 1/3 x. X's times x's product rule. If we don't have x's times x's, you don't use the product rule. So we need the slopes of secant. Secant x, tangent x are the slopes of secant. Times tangent x. This is the product rule. Slopes of the first times the second plus slopes of the second. Secant squared x are the slopes of the second. Don't forget to multiply by the first. You could factor out a secant x. You could multiply all of the guys together if you want to. Leave it like that. Factor out. Somebody's peeking through my window and then giggling. There's no giggling in the hallways. There might be some sort of trig identity that requires you to know. In this class, the only trig identity you're really required to know is sine squared plus cosine squared equals 1. That's the Pythagorean theorem with the unit circle. The hypotenuse is 1. Okay, I'm writing this. Again, we simplify to then take the derivative. I have a product, 1/3 x times cosecant x. Slopes of the first times the second, plus the slopes of the second, slopes of cosecant or negative cosecant cotangent, times the first. Okay? We need to be able to plug values into all of these slope formulas. Remember, plug in x's, get m's into f primes. Now, let's do these because this is going to help us for the end of this lesson with our notational derivatives. When we have like just f, we need to be able to write what its derivative is. Now, again, it's not x's times x's, just 3 times x's. Leave the 3. The derivative of f is the slopes of f. This would be the notational derivative of 3f of x. F of x over 3, I would write 1/3 times the slopes of f. Now, if we have x's times x's, let's look how this notational derivative will show up. Slopes of the first times the second plus slopes of the second times the first. See how that goes? I don't have the slopes of f. It's slopes of x squared times just f. Slopes of f times x squared. If you'd like to, you could factor out an x, but you don't have to / won't need to. I actually don't like that, so just leave it like that. Later, we're plugging in values into this. Here, x's over x's, we have to use the quotient rule. Did we have any quotient rules anywhere here? We didn't have any quotient rules at all here. So don't forget the quotient rule. Slopes of the top times the bottom. You can't multiply these x's together. Don't try. Minus the slopes of the bottom times the top. All over. The bottom squared. X squared squared. Is x to the fourth? Maybe you could factor out an x from the top and cancel with an x on the bottom. Only simplify fractions if it's factored, if you have products. Never simplify over addition. It never works. Okay, now we talk about higher order derivatives, slopes of slopes, slopes of slopes of slopes. Let's do the easy one here. Again, I love how I'm showing you this, like x cubed over 3. I'm going to start by being like, oh, that's just 1/3 times x cubed. It is not x's divided by x's. It's not x's times x's. We don't have to use the product or the quotient rule. A lot of you students who like just copy stuff down, you never get this like into your brain, and like you mess up on later quizzes and tests and stuff like that, questions that involve something like this. So hopefully you're watching this and it's getting into your head now because it's so important. Unless you have x's times x's or x's divided by x's, you don't have to use the product or quotient. The first derivative will be x squared because the 3 gets multiplied by the 1/3 minus the 8x. The second derivative, the slopes of the slopes will be 2x minus 8. Be careful, if I gave you this was the first derivative, you'd only have to take the derivative once to get the second derivative. I think I have a question hopefully later that deals with that. Why slopes of slopes can sometimes be difficult is because when you take maybe the slopes one time, you're just like, okay, the slopes of cosecant are negative cosecant cotangent. But when you take the slopes a second time, all of a sudden you realize, oh, shoot, I have x's times x's. I have to use the product rule. So just be careful. Rules will sometimes show up and then disappear depending on what you have. Like maybe you're using the product rule first and then you don't have to use the product rule again. All dependent on the situation. All right, slopes of the first. I'll have positive cosecant cotangent because I have that negative that's going to cancel with the negative, which is the slopes. That's the slopes of cosecant, negative cosecant cotangent, opposites, times cotangent, plus slopes of cotangent or negative cosecant squared times negative cosecant. Very similar to like secant tangents derivative that we did earlier. We get cosecant x cotangent squared x. We'll get positive cosecant cubed x. And you can factor out a cosecant if you want. Cool. This is always a fun one. First time you guys saw it, you're like, what? And then you realize it's not that bad. Trig functions, like sine or cosine, you take the derivative 4 times, you're back to where you start. Now, that's not something you have to memorize. Oh, I need 4 derivatives. It's just something you should be able to do. Like if I take the derivative 4 times, I'm back to cosine. Okay. Every 4th derivative is cosine. Well, that means the 48th derivative is cosine. The 49th derivative is negative sine. The 50th, 52 is divisible by 4. 50th is that. 51 is that. 52 is that. Ha ha ha. 40, 12. Yeah, that makes sense. Okay, so like that's the 48th derivative. Here's a good one. I'm giving you dy dx. This is already a first derivative. I'm asking you for a third derivative. You only need to take the derivative 2 more times. I start out with x's times x's. So I have to use the product rule. Derivative of the first times the second plus the derivative of the second times the first. When I take the derivative of this, a lot of people mess up because this is kind of 2 derivatives in one. I have the derivative of sine x times 1. All right, well, I don't really worry about the 1. The derivative of sine x is just cos x. That's actually a good way to explain the constant multiple rule. It's like, what's the derivative of sine? It's cosine, right? Well, would you treat the derivative of 1 times sine any differently and say the slopes of 1 are 0? No. So that's my first derivative. The left side's derivative is just cosine. The right side's derivative, think of it as a different derivative. Like it's a new question. The right side's derivative involves the product rule. I have to find the slopes of the first times the second plus the slopes of the second times the first. This is all tricky stuff, guys. Like this lesson is just like, hey, how are they going to trick us? I can combine the cosines, and then I could maybe move the x in front of the sine x, negative x sine x. Cool, another one like this where I'm giving you the first derivative. I'm asking you for the fourth derivative. So take the derivative once, you get the second derivative. Use notation too. Like, I know you don't like to, but later in this lesson you have to. Take the derivative again, you get the third derivative. Take the derivative again, you'll get the fourth derivative. Okay. This notation means third derivative. Don't have to use the quotient rule here. 1 over x, x to the negative first. The first derivative will be 2x minus 1x to the negative second. I'm not going to simplify this because I'm going to be taking the derivative again. 2 plus 2x to the negative third. Negative 2 comes down, subtract 1. Third derivative, this guy goes away. This one goes negative 6x to the negative fourth. So it's the deal with polynomials that if it's a whole number, eventually your slopes of your slopes of your slopes will be 0. If it's anything else besides a whole positive number, anything else besides a whole positive number will be something that you'll have to keep taking the derivative for. If you have a fractional power, you'll have to keep going. A negative power, you'll have to keep going. Okay. Moving on to more tricky questions. What does it mean to be differentiable? Well, we were talking about, hey, you got to be continuous and you got to be smooth or no sharp points. Typically, we don't have functions that we graph that have sharp points, except for our friend, the piecewise function. Piecewise functions sometimes don't even connect. Piecewise functions sometimes connect, but when they connect, they create a sharp point. What we're going to both check, and then ensure is, do our piecewise functions connect? And then when they connect, do they connect smoothly? This is how we are tested on understanding differentiability. We need to connect and connect smoothly. So the first questions are these differentiable? Well, we have to check that they're continuous. Checking that they're continuous, I'm just going to show the limit notation twice, and then I'll stop, is at the point where we're leaving one and picking up the other, will we have the same y values? Continuous is checking to make sure the y's are equal to the y's at our special connecting x point. I plug in 2 to the top and 2 to the bottom. I get 4 equals 4. Okay, good. We connect. Now, the second thing is, do we connect smoothly? Or do we create a sharp point? Now, to check this, and this is kind of going along with Newton's limit and slope marriage, both sides to the left and to the right, their slopes will have to be the same. Now, this is new to our understanding of piecewise functions. We haven't looked at their slopes yet. Okay? What we want is to check, do the slopes of this guy match the slopes of this guy, which means when we connect our two pieces, they don't connect and create a sharp point. Rather, they connect and keep going smoothly on to the next one. So we will take the derivative of the top piece. We will take the derivative of the bottom piece. This is just 4. We will check to make sure the slopes at 2 will equal. And if they do, hooray, this function is differentiable. Very cool. mean, give it to them, right? Very strange. Yeah. Now, I don't like how we're getting the same y value and the same slope value. That's not always going to happen. So, like, this could have been 8 and 8, and then we'd be fine. It's like all 4 values don't have to equal. I hate when we get the same values. That hopefully won't happen again. Here's the other notation that I'm going to show, and then I'm just going to do it. So here, do our slopes equal our slopes? Do our m's equal? Are we continuous? Now, this is important. I'm not looking at 2 here. I'm looking at our special point where we leave 1 and pick up the other 1. Do our y's connect? I get 2. I get 4. No. Immediately I say not differentiable at 2. Sorry, at 1, because we're not continuous at 1. We could check the slopes just to make sure we are understanding the whole process. Check the slopes. We get 2x equals 2. If I plugged in 1, I get 2 equals 2. The slopes meet up, but we don't care. The pieces don't meet up. We get this x squared plus 1. We get this 2x plus 2. If they did meet up, it would be smoothly connected because the slopes are the same. But since they don't meet up, we don't have a tangent slope. Okay? All right, now I'm just going to kind of go for it. Do the y's meet up? So do my y's equal my y's. I get 8 equals 24 minus 4. That's just 20. No, they don't meet up. So no, not differentiable at x equals 2. Check this one. Do my y's meet up? 9, 10, 6, 10. Okay, so I get 10 equals 10. So yes, the 2 pieces meet up. Do our slopes at x equals 3 meet up? These are our y's at x equals 3, our important value. I get 2x equals 2. Unfortunately, at 3, this is 6 equals 2. They do not. So we do connect, but we connect sharply. This first piece has a slope of 6. The second piece has a slope of 2. We have this sharp point. We are not differentiable at x equals 3. We connect, but we don't have the same slopes. So we only had one where it worked out. Well, for the other ones, we're going to make sure it happens, okay? We will make sure that our 2 functions connect, and when they connect smoothly, all right? Now, the second piece is the one that everybody has difficulty with, the m's equaling our m's. So let's just focus on that part. We have plugged in 2 in for x before. This is 4 times 3 is 12. Cool. I don't know what a or b is. I could subtract 5 from both sides, but let's leave it here. But now, my slopes of the top and the slopes of the bottom must be the same at 2. A and b are numbers. This is very important. That's a number. That's a number. Think about replacing it with a number and taking the derivative of that. If it was 4x plus 5, the slopes would be 4. Ax plus b slopes, or ax plus 5 slopes, are a. You don't have to plug in 2. We don't have an x. 3x squared plus b slopes are 6x plus 0. The slope of b is 0. Now, don't forget, it's the slope at 2. When x is 2, I plug in 2 for x. I get a equals 12. Once I get a is 12, 24 plus 5 equals 12 plus b. I'll get b is equal to 12, 30, 40, 50, 60, 17. Okay, to ensure that these 2 pieces meet up and smoothly, you got to have that for a and that for b. Next one, my y's will have to meet up at x equals 1, and our m's will have to meet up at x equals 1. So 2ax plus b, whoops. Let's just do y's. Plug in x equals 1. A plus b has to equal 3. Great. M's, 2ax plus b has to equal 0. The slope of 3 is 0. The slope of ax squared is 2ax. The slope of bx is b. At x equals 1, don't forget that. I get 2a plus b has to equal 0. I have two equations, two unknowns. Let's solve for b. Let's substitute in. A has to equal -3. 2a minus a is a. Subtract 3. A is -3. If a is -3, b has to be 6. Our x coordinate is -1 now. A minus 3 equals b plus 2. Plugging in -1, a minus 3, b minus -2, b plus 2. Slopes. 2ax equals -2. Plugging in -1, -2, a equals -2, a equals 1. If a equals 1, 1 minus 3 is -2 equals b plus 2, b equals -4. This one ends up not being very nice. I think this equation up here has to be like 0 plus b, or whatever. The important x value is 0. B has to equal 5. I plug in 0, I just get b. The cosine of 0 is 1. A has to equal 0. The slopes of 5 cosine, -5 sine. Plug in 0. A is 0. B is 5. Cool. Moving on to table problems. Okay. Notational derivative problems. This is what you're thinking of. This is just like making sure students are comfortable using notation in future math classes. If you take higher level math classes, there's no numbers or polynomials. It's all just notational. So this is like a good way to make sure you're comfortable writing down notation, because in the future, that's all you have. The derivative of g is g prime. The derivative of f is f prime. That's it, right? You're trying to find k prime of pi. Okay, I'm going to take the derivative. I'm going to look at the slopes of k. Well, k slopes are k prime. There we go. I have k prime. G slopes are g slopes, g prime. F slopes are f slopes, f prime. These are not equations. This is a big mistake for a lot of people. This is not f times x. That's not it. This is not some sort of product. This is the function f that uses x's. This is notation for f using x, not f times x. You don't think of this as f times x. I know you guys are all like, when I see parentheses mean multiplication. Not with function notation. This is just f of x or f using x. F using x's derivative is the slopes of f using x. You could honestly just get rid of the using x and say that F's slopes are F prime. I could have just said G and F. G slopes are G prime, F slopes are F prime. That's fine. To be proper, you need of X. But if you're asked to find K prime of pi, well, you should be thinking, okay, I want the slope of G at pi. This is why we kind of use the X's so we can see, oh, K's slopes using X's equal G's slopes using X's plus F's slopes using X's. If I plug in pi, I get that. Now, on this page, you're given the information. On the next page, you have to get the information from a graph that you see. I can look here. When X is pi, G prime is -4. F prime is -1. And we get a numerical answer here, -5. Okay? We don't have any equations to help us. Don't think of it as F times. It's just F, the equation. F using X's. Just like we talked about before, if you have a number times a function, if you have something divided by a number, you don't have to use the product or the quotient rule. Don't. You could, but it's not necessary and you're probably making mistakes. The slopes of P will just be the constant 3 times the slopes of F. It's not F times X. It's F using X. F's slopes are F prime. We don't have to use the quotient rule. We could rewrite this as 1/4 times G. It's the same as G over 4. The slopes will be 1/4 times G prime. Plugging in 2, I get 3 times F prime of 2 plus 1/4 times G prime of 2. F prime of 2 is -2. G prime of 2 is -1. I have -6 minus 1/4. That's -24/4 plus -1/4. Multiply the top and bottom by 4. And you get -25/4. Okay, it's a good start. We feel good about ourselves. We're like, okay, I got this. Notational derivatives, no big deal. And then we get to all the other ones and we make huge mistakes unless we actually do our homework and pay attention. So let's see. Are you actually doing your homework and paying attention? The remaining ones require you to use rules. For example, it's not 2G plus F. It's 2G of X times F of X. Product rule. Now, there's 2 ways to handle the 2. You could either leave the 2 out or you could bake the 2 in. Here's what it looks like. If I left the 2 out, I could just say, well, J's derivative, and this is where I'm going to get rid of the of X just to make it easier to see. J's slopes will equal. I'm going to leave the 2 out, and then I'm going to look at the slopes of G times F. That will be the slopes of G times F plus the slopes of F times G. Now, if I want to find J prime of 2, I get all my information from my table. The other way to do it is to bake it in. What do I mean by that? Is say, you know what? Don't leave the 2 out. Just put the 2 in with the G. So you could say the slopes of J are the slopes of 2G, which are 2G prime, times F, plus the slopes of F times 2G. What you'll notice is that they're the same, just this, you could distribute the 2 in. This, the 2 is automatically distributed in. It's up to you. I think in the future it helps to bake things in. versus leaving things out, but I'm not going to judge. If I'm finding j prime of 2, I'm going to use this one. 2 times g prime of 2 is -1. F of 2 is 4. F prime of 2 is -2. G of 2 is 3. So I get 2 times -6 plus 4 is -10. So I get -20 as my answer. Okay? I'm going to have to get the homework to pull up these numbers. X's times X's. The slopes of X times G's function plus the slopes of G times X's function. If you want to get rid of the of X, it's totally fine. Okay. Let's look. I got G of 3 is 4. G prime of 3 is -2 times plugging in 3 for X. 4 minus 6 is -2. X's divided by X's. Derivative of the top times the bottom minus the derivative of the bottom times the top, all over the bottom squared. I'm debating whether I need to show the of X, and I'm thinking I don't. Prove me right. I think the last one would have helped if you showed of X, because like we are plugging in 3 for X. So it's G at 3. It's G prime at 3, and it's X at 3. Hopefully we understand that. Okay, 4, G prime of 4 is -3. F of 4 is 3. F prime of 4 is -4. G of 4 is 2. F of 4 is 3. 3 squared is 9. I got -9 plus 8 over 9. -9 plus 8 is -1 over 9. Cool. Yo, you see that 2? You could pull out the 1/2. You could leave it out. You could bake it in. I'm going to leave it out. It'll be a little bit easier to do the calculations. Slopes of the top times the bottom minus slopes of the bottom times the top, all over the bottom squared. Plugging in 2 for X, I get 4. I got F of 2, 4. F prime of 2, -2. 2 plugged in for X squared, 4, over F of 2, 4 squared, 16. 16 plus 8 over 16. 16 plus 8 is 24. 12 sixteenths. 12 sixteenths is 3/4. Divide the top and bottom by 8. X's times X's. G's slopes times cos plus cos's slopes times G. Again, the of X doesn't really mean anything. It doesn't mean it's a product. It's just using X's. So I can get rid of it. I hope we're cool with it. It's just like a shortcut, which sometimes is bad. At pi, G prime of pi, -4. Cosine of pi, -1. Sine of pi is 0, so I don't care what g of pi is. My answer is just positive 4. X's times x's again. Derivative of the first times the second plus the derivative of the second. I'm bringing the x's back because this is easier to write. Times the first. And I'm also showing you, like, what is it going to look like? 6 times 3 times g of 3. I'm plugging in x wherever I see it. If you did not understand what I was doing in the previous ones, go back to using of x's. 6 times 3 times g of 3. G prime of 3 times 3 squared. A lot of 3's. G of 3, this is going to be a big number, is 4. 6 times 3 times 4 plus g prime of 3 is negative 2. Don't mess up on arithmetic. Take your time. I'll do 24 times 3, 72. This is negative 54. This is 18. Cool. All right. The remaining questions, I'm giving you a graph. Okay, this is the graph of G and F. G's in red, F is in black. For this remaining set of questions, you need to understand the following pieces of information from the graph. Like, what is F of negative 3? Okay, this is like the Y value, and this is like remembering lesson 1 and lesson 2. This is the Y value. Plug in X's into functions, get their Y's. Plug in X's into slope equations, get M's. Cool? So let's look at X equals negative 3. 1, 2, 3. This is negative 3. Let's look at the Y value and the slope. I can find both of those. I can see the Y value is the Y coordinate 1. I can see the slope is the slope of this line segment, which can be calculated by rise over run. Or you can use the slope formula. It's exactly negative 1. Got it? So these table problems require you to understand the notation, not just find it, and not just get stuff using a table. Okay? Cool. At negative 3, let's look at G. G's y coordinate is 2. G's slope is 0. G's y coordinate is 2. G's slope at negative 3 is 0. Let's look at 1. F's y coordinate is negative 1. F's slope is 0. G's y coordinate, 1, 2, 3, 4, is 4. G's slope is positive 1. 1, 2, 3, 4. What's up? You're being recorded right now, so speak carefully.
Okay, for this one, because I took for continuity, so I did the ax squared, and then I plugged in negative 1.
Cool.
So then it's like minus a.
No,
sorry, a minus 3.
got it.
And then I got I plugged in this here, and then I got b plus 2. So then I said a minus 3 equals b plus 2.
Cool.
And then I got
Nothing.
Yeah.
Continue.
And then I did the sharp point 1.
Yep.
And so then that's just 2a minus nothing. And then nothing.
2ax.
2ax. Yeah.
Okay.
Oh, that's what I did wrong.
X squared slopes are 2x.
That's what I did wrong.
Cool.
Okay, cool. Thank you.
Yep. F slopes at 4, F's y coordinate at 4. 1, 2, 3, 4. F's y coordinate is 1, 2, 3. F slopes are up 2 over 1. The slope of this line segment is 2. G's y-coordinate is -1. G's slopes is down 1, 2, 3 over 1. G's slopes are -3. Fun. 3.25. Good question, Mr. Messer. Again, it's f divided by 2. You don't have to use the quotient rule. You could just write the 1/2 times f, and its slopes are 1/2 times f prime. The slopes of g are g prime. You want to use notation, use it. G prime of f of x. It's not a product. 3.251 to 3.25 is like right there. Okay, all I need to know is what is the slope of f and the slope of g. Well, we found the slope of g was -3 at that location for this entire segment. The slope of f was +2. Boom. 1 plus -3 is -2. That's my answer. You don't have to use the product rule here. The slope of 2f is 2f prime, just like the slope of 2 sine is 2 cosine. The slope of 7g is 7g prime. Done. At -2, the slope at -2 of f is -1. The slope of g at -2 is 0. There's my answer. The slope of g at -2 is 0. G prime is the slope of g. Careful. Now we have x's times x's. Slopes of f times g plus the slopes of g times f. Plugging in 1. F of 1 is -1. G of 1 is 4. G prime of 1 is +1. F of 1 is -1. We got -4 minus 1, -5. X's times x's. The derivative of x is 1. The slopes of x are 1 times f plus the slopes of f times x. Plugging in 3. 1 times f's y-coordinate at 3. 1, 2, 3. F's y-coordinate is 1. F's slopes at 3 are +2 times x at -3. It's very important. It might help to have the notation of x's here. I could see people make mistakes. Now we have to do f of 3, f prime of 3. It's not times 3. It's like, what is the value at x equals 3? It really helps us understand function notation, honestly. Times 3. It is easier for quotient rule especially to leave out the 3/2, because then you don't have to square 2 and f of x in the bottom. You just have this. So you can leave out the 3/2. You could bake in the 3 and the 2. It'll work out. It'll just be a little bit messier. Slopes of the top times the bottom minus the slopes of the bottom times the top, all over the bottom squared. At 1. G's slope at 1 is 1. F's slope at 1 is 0. That's nice. That's not right. Slow down. G's slope at 1 is 1. F's y-coordinate, this is just f. F's y-coordinate at 1 is -1. F's slopes at 1 are 0. G's y-coordinate is 1, 2, 3, 4. F's y-coordinate at 1 is -1 squared is 1. Giving me 3/2. This is 0. No, this is times. This is like, it's like, you gotta, like, look at me. I'm making mistakes because I'm not being careful. We're multiplying these things together. I had 1 times -1. If I wrote 1 minus 1, all of a sudden I'm thinking that I'm subtracting. I just made a stupid mistake, Like, pay attention, Mr. Messer. 3/2 times -1. You could leave out the 2. This is easy enough that it's like easy enough to bake it in. So I'm going to bake it in. What do I mean by bake it in? Keep 2x together. Slopes of the top times the bottom minus the slopes of the bottom times the top. All over the bottom squared. At 4, g of 4, g prime of 4, 4 times 2 is 8. G of 4 squared. Okay, g's y coordinate at 4 is -1. So I get -2 minus g's slope is -3 for that line segment. Down 1, 2, 3. -3. Times 2 times 4. G's y coordinate at 4 is -1. Squared is 1. So I got -24 becomes a positive 24 minus 2 is 22. All right, last 2. Oh, this one gets everybody. I don't know why. I feel like this will get you all. No product rule, product rule. It's one of those 2 things in one. 3f's slopes are 3f prime. X squared g of x slopes are 2xg plus g prime times x squared. Plugging in 1. I need f slopes at 1, which is 0. That's nice. 2 times 1 times g's y coordinate at 1. That's 4. G's slopes at 1 are 1 times 1 squared is 1. So I have 8 plus 1, which is 9. You should feel really good if you're getting these questions right. You can either distribute the x to simplify first before you take the derivative, or you can use the product rule right away. I'm going to use the product rule. X's slopes are 1. 2f minus 3 slopes are just 2f prime minus 0. Slopes of 3 are 0. This is a tricky one. Plus 2f minus 3 times the slopes of x. First slopes times the second. Oh, shoot. I am making so many mistakes here. First slopes times the second. This is a product. Plus second slopes times the first. Plugging in -1. F of -1. Oh, this is a good one. I like how we're doing this. F of -1 is -1. This is times. That's minus. F prime of -1 does not exist. There is no slope at that sharp point. This answer actually does not exist. Now, I'd never give this to you on a quiz or on a test, just because it's not fair sometimes. But I don't know, it sometimes shows up. You're understanding that, oh, actually I can't do this problem because I don't know the slope here. So that's why it doesn't exist. All right. Tricky stuff, guys. I'll give you the formulas for your quiz for secant, cosecant, tangent, cotangent. You're in charge of knowing higher order derivatives. That's the second thing. You're in charge with these differentiability questions, and you're in charge for these notational derivatives. 4 different things, all tricky derivatives. That's lesson 4. Peace.